So I've had some questions on Lab 9, the types of chemical reactions. So I was going to make a supplemental video. What I'm going to do is I'm going to work through the pre-lab on page 49 of your lab manual. So I'm going to go through naming the types of reactions, go through how to balance the equations, and then also go through ionic, net ionic, and then the redox reactions, how to tell what's oxidized, how to tell what's reduced. So I'll be working through the pre-lab for you. You still need to turn in the pre-lab. No one should get anything wrong in the pre-lab because I'm about to do it. And then everything you learn in the pre-lab you can apply to the lab portion because it's the same steps for all parts. So let's start by looking at the 7 nonmetals that exist at diatomics. So grab my chemistry folder here. What is a diatomic? So a diatomic, di meaning 2. Atomic, atoms. So it means 2 atoms combined. So on your periodic table, there are 7 nonmetals that exist as diatomics in nature. What that means is they don't exist by themselves. They find another atom of the same element and then pair up to form a bond to make them more stable. Okay, so an example of this would be hydrogen. So if you look at hydrogen, I have it highlighted in green on my periodic table here. It's number 1. It's got 1 proton. So hydrogen, you'll never see just one hydrogen atom floating around. What it does is that hydrogen atom finds another hydrogen atom and then they pair up to form a bond. So the chemical formula of hydrogen in nature is H2. So this 2 meaning that 2 atoms of hydrogen are together. So since there's 2 atoms, it's diatomic. Okay? So the structure of it would be a hydrogen, single bond attached to another hydrogen. Now hydrogen isn't the only nonmetal that exists as a diatomic. There's actually 7. And so hydrogen's way over here by himself, but the other 6 actually form the number 7 in your periodic table. So if I could get a little bit closer with this. You can see the highlighted 7 that I made there. So those 6 other atoms also form diatomics in nature. So nitrogen, and then going across to oxygen, fluorine, and then down the halogen list there. So I have one of them listed. Nitrogen forms N2, diatomic in nature, and so it's your job on that one to name the other 5. I have 2 of the 7. Okay, so you can use the highlighted picture I just showed to get the other 7. Or the other 5 of the 7. So now let's look at types of reactions. Okay, so there's 4 classification types given to you in this lab that you're going to need to use to classify the reactions. So the page 51 has the reaction types and the generalized equations. I talked about these a little bit on that PowerPoint video, but now I'm going to apply them to actual examples and go through all the steps of balancing and all of that. So the first type that you see on that list on page 51 is the synthesis or combination reaction. So when you're approaching a chemical equation, how to tell if it's a synthesis or combination is you will have 2 elements combining to form 1 product. So the key here is 2 reactants, because this is the reactant side of the equation, and only 1 product. So when you see that, 2 reactants, 1 product, that should automatically tell you, okay, this is a synthesis, this is a combination. Because what we have in this specific example is aluminum and chlorine. Notice chlorine is one of those diatomics that exists as a diatomic in nature, Cl2. So we have aluminum and chlorine, and they come together to form a bond to form 1 compound as the product, aluminum and chlorine combined. Okay, so that's why it's called a combination. They combined together. So given this equation, let's point out a few things with it. Let me get some different colors to help with this. So first off, you might notice these little letters at the end of each element or compound. So these letters are representing the state of that matter. Okay, so if you see an S, What the S is telling you is that that's a solid. So the person that did this reaction, they took a solid piece of aluminum and put it in the flask. If you see a G, G stands for gas. So in this particular reaction, they had a solid piece of aluminum and then they pumped chlorine gas into most likely a covered beaker or test tube, so the gas couldn't escape. The other two versions you'll see as we come up is you might see an L present after the element or compound, and this is a liquid. So what that means is it's in its pure form. It's not mixed with anything else. We'll often see water with an L by it, because that means that pure water was added to the reaction. The last one you'll see is an AQ. So what AQ means is aqueous, and this is a solution. So what that means is it's a solid dissolved in water. So for instance, to make salt water, you would take sodium chloride, NaCl, add water to it, and what would happen is that solid sodium chloride, that salt, would dissolve in the water. When it dissolves in the water, you now have a solution, and that would be represented with an AQ by it, saying that that solid dissolved in the water. And we'll look at an example of this when I talk about the other two types of reactions. Okay, so let's continue focusing on this synthesis one though. So now we know how to identify. It's two reactants combining to form one product. We now know what these little letters mean after each element or compound. So now let's balance the equation. So when I balance the equation, the way I like to do it best is I make a list of all the elements on both sides of this arrow. Because the goal in balancing it is to get the same number of atoms on both sides. So I need a certain amount of aluminums here, the same amount of aluminums on the product side. You kind of go back and forth, adding numbers in these empty spaces as coefficients to change the atom count. Okay, so I'm going to start by writing my list. I have aluminum and I have chlorine. On the product side, I also have aluminum and chlorine. So how many of each? I want to see how much I have right away to see if it's balanced. So right now, I have one aluminum. How do I know it's one? Because there's no subscript after it. If there's no subscript, that means there's just one. Looking at chlorine, there's a subscript of 2 after it. So what that tells me is there are 2 chlorine atoms. So on the reactant side right now, I have 2. Going over to the product side, for aluminum, once again, no subscript, so it's just 1. For chlorine, now I have a 3 on the reactant side, so that means I have 3 chlorines on the reactant side. So now I check to see if it's balanced. Looking at my aluminums, they are. I have 1 on each side. That's good. But looking at my chlorines, they're not. I have 2 on the reactant side, right? But I have 3 on the product side. And I need them to be the same on both. So I start by adding numbers in. So I need more chlorines. So if I go ahead and put a 2 here, what that does is it makes me have 4 chlorines. So how do I know that? To figure out the total number of atoms, you take the coefficient and you multiply it by the subscript on that element or atom. So what I'm doing to figure out I have 4 is I'm taking 2 and I'm multiplying it by the subscript of 2. So that now tells me I have 4. Okay, well it's still not balanced, right? Now I have too many on the reactant side and not enough on the product side. So the only thing I can do is add more on the product side. And I can only put whole numbers here. I can't put a half. It has to be a 1, a 2, a 3, a 4. So I start by putting a 2 there. Okay, you always want to start with low numbers and work your way up. Now if I put a 2 here, that changes my chlorines, 2 times the subscript of 3 to 6. But notice, it It's also going to change my aluminums because this coefficient is representing every element in that compound. So to figure out my aluminums, I take coefficient of 2 multiplied by the subscript 1. So 2 times 1 tells me I have 2 aluminums. All right, so let's go back again. So now notice I have 2 aluminums, 6 chlorines. So I need 2 aluminums and 6 chlorines on my reactant side as well. So let's change the coefficients to try to get that. So I'm going to change my 2 in front of my chlorine. So what number can I put here so that I have 6 chlorines? What times 2 gives me 6? 3. 3 times 2 gives me 6. So now my chlorines are balanced. Good. Let's balance my aluminums. I have 2 on the product side and just 1 on the reactant side. So if I want to, I just put a 2 here. 2 times the coefficient of 1 gives me 2. So now it's a balanced equation. So coefficients of 2, 3, 2 give me balanced. I believe that's all I needed to do for that one. Name the reaction type, yes. Balance, yes. Okay, so let's look at the decomposition now, a different type. So how do you tell decom? Notice it's the opposite of synthesis. Okay, decom, I have 1 reactant decomposing, breaking apart into 2 products. Okay, so 1 reactant, 2 products, that tells me it's decom. So my next step is to balance. How do I balance? Write a list. Write what you got. So I have K, potassium, I have CO, chlorine, and I have O, oxygen. Same thing over here. I have potassium, I have chlorine, I have oxygen. Now I'm going to write how many of each I have. Looking at the coefficient, or sorry, the subscripts. So I have 1 potassium on the reactant side. Chlorine, also 1. Oxygen, well there's a 3 after it. Now moving over to the product side. 1 potassium, 1 chlorine, 2 oxygens. So my potassiums and chlorines are balanced. I have 1 of each on both sides. Oxygen, not so much. Okay? So whenever you have an odd number of an element, it's probably best to try to get an even number. Why do I say that? Because no matter what, on this side, there's no way I'm ever going to get an odd number of oxygens. Because anything times 2 is going to be an even number. If I put a 1 there, which is what's there right now, I have 2 oxygens. If I put a 2 there, I'm going to have 4 oxygens. If I put a 3 there, I'm going to have 6 oxygens. Kind of see where I'm going with this? So I'm always going to have an even number of oxygens on here. I'm never going to have it odd. So my first step is I'm going to make this even, because that way I'm not going to go back and forth as much. So how do I make that number even? Well, if I just put a 2 here, that changes my oxygens. Remember, coefficient times the subscript, so 2 times 3. Now I'm going to have an even number, 6 oxygens. But notice, when I put a 2 here, it doesn't just affect the oxygens, it affects the potassium and the chlorine as well. So how many potassiums do I now have? Coefficient times subscript, so 2 times 1. Now I have 2 potassiums, and also 2 chlorines. So now let's go to the product side and try to get this balanced. Let's start with the potassiums. I have 2 on the reactant side. I want 2 on the product side. So what number, what coefficient can I put here to get to? Just a 2. 2 times 1 gives me 2 potassiums. This is also going to affect my chlorines, which is good, because 2 times 1 gives me 2 chlorines as well, and I needed 2. Now their chlorines are balanced. Oxygen's all that's left. I have 6 on the reactant side. I need 6 here. So what number, what coefficient can I put here that would multiply by 2 and equal 6? 3 times 2 gives me 6. So now everything's balanced. 2 to 2 to 3. So we have 2 more types to look at. The next one is single replacement. Reaction. So the example of a single replacement reaction on your pre-lab is the silver nitrate example. So we have AgNO3AQ plus zinc, giving us solid silver plus zinc nitrate. So this is an example of a single replacement reaction. So let's talk about some aspects of single replacement reactions. Well, first off, let's look at the letters after each element or compound. So AQ, remember I said that means aqueous. What that means is I have silver nitrate dissolved in water. It's a dissolved solution, a soluble solution. Okay. Then I add a solid piece of zinc to that. I get a reaction. What comes out is solid silver, and the zinc nitrate is aqueous. Forgot the AQ there, which means zinc nitrate is now dissolved in the water. All right, so how do I tell it's a single replacement reaction? With single replacement, you always have a compound. So 2 or more elements combined form a compound, reacting with an element. So this is an element by itself. It's not attached to anything else. It's zinc, pure metal. Okay? So I have a compound, 2 or more elements combined, reacting with an element by itself. And what's happening is we're switching partners. So zinc is the metal. Okay? Silver is the metal portion of this ionic compound. So the metals, in this case, are going to switch partners. So what that means is zinc is going to take the place of silver so that now it's with the nitrate ion. That's what we have over here. Zinc, now with the nitrate ion. Since it kicked silver out, now silver on the product side is the metal by itself. All right? So, identify compound reacting with element, leaving an element by itself, and a new compound. So the next step, let's balance this guy. So to balance, same steps, but a slightly different because I want to point something out here. We have a polyatomic. So whenever you have a polyatomic, those are the ions. You probably got a table during lecture. I can also post a table on Blackboard of common polyatomics. What they are is covalently bound elements that have an overall charge. So this NO3, this is actually called the nitrate ion. So when I'm balancing, when I have a polyatomic, I'm not going to split it up. What that means is I'm not going to put nitrogen and then oxygen and do a separate list. I'm going to keep that NO3 together because it's going to make my life easier. Okay. So I have silver, nitrate, and then I have zinc. Over here, I also have silver, nitrate, and zinc. I'm just keeping them in the same order. Oh, forgot the NO3. All right, so now how many of each do I have? Silver, there's no number after it, so I just have 1. The nitrate, the NO3, okay, there's no number after it. So imagine parentheses around this guy, and there would just be a 1. That's saying there's 1 NO3 ion. For zinc, I just have 1 as well. Now let's look over here. Silver, 1, NO3, so this time notice the NO3, it has parentheses around it, and then this 2 after it. So that 2 is saying there are 2 NO3 ions. So on this side there are 2. For the zinc, just 1. Alright, so silver and zinc are balancing on both sides. It's the NO3s that aren't. I have 2 on the product, I need 2 on the reactant. So if I put a number 2 here, that changes my NO3s to 2. But notice it's also going to change my silver. My silver now has 2. So now I need to go back over to the product side and change my silver. So what number can I put here to make it 2? Just a number 2. 2 times 1 is 2. So now it's balanced. It would be a 2 to 1 to 2 to 1. Now you don't have to put 1s in these empty spaces. You can leave them blank. Because if there's no coefficient there, I assume that it's a 1. But you can put 1s there if you want. That's not incorrect either. Okay, so now this guy's balanced. But you have to actually do more with him. On number 5, it says for the reaction in 3D, that's what this is. This is 3D on your pre-lab. Assign oxidation numbers to the reactants and products, and then identify the substance being oxidized, oxidizing agent, substance being reduced, and the reducing agent. All right, so what I'm going to do is I'm going to erase this bottom part here where we used to help us balance so that we can write our redox reactions. What that means is we're going to be assigning charges. How do we do that? All right, so silver nitrate, it's an ionic compound. Ionic means it has charges. Metal is always positive, it's always a cation. The non-metal, or the polyatomic portion in this case, is negative. So silver is a transition metal. Transition metals have variable charges. So what that means is, I don't know the charge of silver, okay? I'm gonna have to figure that out by looking at what it's attached to. And what it's attached to is this NO3 ion. How do I figure out the charge of the nitrate ion? You'd look it up in a polyatomic table, okay? So the polyatomic table would have NO3, it would give the name of NO3 saying it's nitrate, and it would also show you that it has a -1 charge. Okay, so I can use this to figure out the charge on silver. Why? Because this compound as a whole is neutral. What that means is the positive and negatives cancel each other out. So if I have a -1 on the nitrate, and I need to cancel out that -1 charge, what do I have to have on the silver to cancel that out? Well, I know I'm going to have a positive, but a positive what? It's going to have to be a positive 1, because +1 plus a -1 equals 0, okay? Neutral. So here are my oxidation states, or also called charges. It's the same thing, oxidation states or charges, for the silver and the nitrate ion. Okay, now let's go over and look at the other reactant, zinc. Zinc is by itself. What that means is any element or atom by itself, its oxidation state, its charge is 0. Okay, that's just a rule. If you see an element or an atom by itself, when it's not attached to anything else, its oxidation state is 0. Moving over to the product side, notice I have silver by itself. What I just say about atoms or elements that are by themselves? Oxidation state is 0. Now let's look at zinc nitrate. So zinc, once again, it's a transition metal. I'm going to put a question mark because I don't know its charge. I have to look at what it's attached to figure out its charge. And it's attached to NO3. And we said NO3 has a -1 charge. I'm going to put -1. But also notice how many NO3s do I have? I have 2, right? We figured that out when we were balancing. So I have 2 NO3s. So 2 NO3s and 1 zinc. So my total on the negative side is going to be -2, 1 from each of the NO3s. So what am I going to have on the cation on the positive side to cancel out that -2? -2 plus a +2 will give me 0. So that means the charge on this zinc, since there's only one of them, has to be +2 to offset both of those NO3 ions. So why do we need to know the charges? Because for redox, I'm going to write that over here, redox reactions, we have, I like to use the Leo the Tiger Says Grr, I gave you a few of them. So that's losing electrons is oxidation, and then gaining electrons is reduction. So I'm going to look at a scale here. We have 0, our neutral, then we have -1, -2, -3, +1, +2, and +3. So what's happening is, if you are moving up the scale, so you are going up, this is going to be oxidation. You are going down the scale, should use a different color. This is reduction. So what this list right here is, these are our oxidation states, our numbers, our charges. And what you need to look at is what's happening from the reactant side to the product side. All right, so let's take a look at silver. I'm going to isolate silver here. So silver's oxidation state is changing from reactant to product, right? So it's going from Ag +1 to neutral. So going over to this scale, it's starting at a +1, starting right here, and it's going down to 0. So what that means is, to go down to a 0, it's gaining a negatively charged electron. So if I'm going from a +1 to a 0, I'm going in the downward direction. So this is reduction. This is the element that is reduced. And these always happen in pairs. One is reduced and another one is oxidized. So what's happening to the other one? So to figure out the other one, you're looking at charges. Notice NO3 is a -1. On the product side, it's also a -1. So its charge didn't change, so it wasn't oxidized or reduced. So we'll take him out of the equation. Nothing happened to him. He stayed the same on both sides. But who changed is the zinc. Notice reactant side, we have zinc at a 0. And on the product side, zinc is a +2. So let's isolate that guy down here. He went from zinc 0 to zinc +2. So now going over to our scale, starting at 0, and he went in the upward direction now to the +2. And if we go upward direction from a 0 to a +2, we are losing electrons to get there, because we're losing negatively charged electrons to become positive. So going in the upward direction is oxidation. So the answer would be the substance being oxidized would be zinc. I guess I can just write that here. The substance being reduced would be the silver. So oxidized, reduced. Now, it also asks about oxidizing agent and reducing agent. So to figure out oxidizing agent and reducing agent, it's the opposite. So what that means is silver nitrate, it was reduced. So since it was reduced, that means it oxidized zinc. So since it oxidized zinc, silver nitrate is the reducing or oxidizing agent. Sorry, write that. So it was reduced, meaning it was the oxidizing agent. This guy zinc here, we just said was oxidized because it lost electrons to go from a 0 to a +2. Meaning it is the reducing agent. So you're going to have to go through those steps for part B, because part B, I believe, that's the one where you're taking copper and oxygen, right? So that's a synthesis reaction. And it's also a redox reaction. So you're going to go through, give the charges on copper and oxygen before and after the reaction, figure out which one was oxidized and which one was reduced. And then whichever one was oxidized, that one is the reducing agent. Right? If it was oxidized, it's the reducing agent. Whichever one was reduced, that's the oxidizing agent. Part C is similar. That one is magnesium with hydrochloric acid. So you have an element by itself reacting with a compound. That is going to be a single replacement reaction. It's also a redox reaction, so you're going to have to list the oxidation states and figure out which one was oxidized and which one was reduced. So use this scale, figure out which direction you're going to help with that. Or you can use these mnemonic devices as well. And then part D is also a redox reaction. So you have to do that as well. All right, so we have one more type of reaction to look at. Let's see what time it is. Got a class in about 10 minutes. Let me try to get through this. And that is double. So double replacement reaction. The example on your pre-lab is sodium chloride reacting with silver nitrate to make sodium nitrate and silver chloride. So double, how do you identify it as double? Compound reacting with a compound. Okay, so no elements by itself. Compound reacting with a compound, switching partners to give two new compounds. Okay, so if you have two compounds on both sides, reactant and product, it's going to be double. Okay, so what do you need to do with this? Well, first let's balance it. So I have sodium, chlorine, one of each. I have silver, and the nitrate ion, notice I'm going to keep that together because that's a polyatomic and I have just one of those. Going over to the reactant side, or product side, sorry. One sodium, one NO3, one silver, one chlorine. Look at that, balanced. 1, 1, 1, 1, done. So the nice thing about double replacements is they're pretty easy to balance. So the reason I'm erasing this portion now is because now that it's balanced, you also need to, in number 4, write the complete balanced ionic equation and the net ionic. So balanced ionic. That means we're going to write the ions of each of these, so each element with its charge. But we're only going to do it, we only have to split it apart into ions if it has an aqueous sign by it. Because if it has an AQ, that means it's dissolved in water, it has separated into its ions. So we will write its ions out separately. However, if it has a solid by it, that means it didn't break apart, it didn't dissolve in water. It's still silver with the chlorine together. So we aren't going to split that one into its ions because it hasn't dissolved in the water into its ions. So for balanced ionic, to write the charges, Na is a +1. How do I know that? It's an alkali metal. Group 1 of the periodic table. All alkali metals form a +1 oxidation state every time. Chlorine, -1. It's halogen. Halogens always form a -1. Looking at silver and nitrate, we actually already saw this one in the previous example. And when we figured out the charges for silver and nitrate, we figured out that silver had a +1 and the nitrate ion had a -1. Okay, so look at the previous example if you forgot how we figured that out. So that's my reactant side. Product side, same thing. I have sodium over here as well. It's a +1, just like on the reactant side. It's an alkali metal, always a +1. I have NO3, -1, just like over here. Now the silver chloride, I'm going to keep together because it's a solid. The rest of these are aqueous. That's why I split them up into their ions, because they are dissolved in the water. So this is the balanced ionic. I have written all the ions out that are aqueous and left the compounds that are solid as a whole. Now for my net, you're using that same balanced ionic equation, except for it's a simplified version. What you're going to do is you're going to cross out any ions that are the same on both sides of the equation. So what do I mean by that? Well, I have a sodium +1 on the reactant side. I also have sodium ion on the product. Since it's the same on both sides, I cancel them. Okay, chlorine, -1. I don't have a chlorine ion on the product side, so I can't cancel him. Same goes with the silver. I have silver ion on the reactant side, a +1, but I don't have the ion on the product side. It's in a compound. It hasn't broken apart on the product side, so I can't cancel it. NO3, those ions are on both sides, so I cancel that. So to write my net ionic, I write what's left. I have chlorine, aqueous, plus a silver ion, aqueous, to form silver chloride solid. So this would be my net ionic equation. When it says also identify the precipitate, precipitate is just a fancy word for solid. So the solid equals precipitate. Okay, so which one's the solid? The one with the S by it. So AgCl would be the precipitate. So I hope this helps with Lab 9. You've probably seen the announcement already. So if you would like to meet virtually, I do have some time on Friday from 11 to 1, if that works. If not, we can try to set something else up over the weekend if you need this explained a little bit more. But this should help at least get you started along with that PowerPoint video. I'll also post some separate videos from YouTube that students in my other chemistry class have found helpful with balancing equations, as well as identifying types of reactions and predicting products. So be on the lookout for those.